Hello, everyone. Welcome to the Richardson RFPD Tech Chat. My name is Stefan Witte. I'm Senior Business Development Manager for Energy and Power Products in Europe at Richardson RFPD. I'm happy to introduce today Steve Roberts from Recom Power. He is Innovation Manager at Recom and has experience in power conversion since decades. Additional, he is writer of 2 books about AC/DC and DC/DC power conversion. Both books are available for free download at the webpage at Recom. Hello, Steve. Thank you very much for joining us today.
Thank you. I'm glad to be here.
Great. So today, Steve, we want to talk about fast switching in high power applications. The usage of wide bandgap products like silicon carbide and gallium nitride becomes more and more important here. So can you explain why fast switching becomes more and more important, especially in high power products?
Yeah, sure. What I'll do here is I've got a slide presentation that I want to show you, and I'll just talk you through it, and we'll just see how it goes. So you should see that now. Basically, it's the need for speed, as I call it. The reason why we're seeing switching frequencies going up and up in power designs is manifold. One of the main reasons we're seeing is that there's a huge need to reduce the size of the power supply. So if you increase the switching frequency, you can improve what we call the power density. That means you get a lot more power in the same size, or alternatively, in the same size, you get 40% more power. And this is all to do with increasing the switching speed, because the other components that you need, such as an inductor or a capacitor, can be made much smaller if you have faster switching. It's basically a direct relationship between increasing the speed and reducing the size of the filters that you need. So that's the driving force behind it all. Everybody wants smaller and more powerful power supplies. And a 40% increase is something special, and that's why really wide band gaps are really becoming very, very popular, and why there's so much interest in them. The other thing is the higher overall efficiency, because if you have a higher frequency switching design, it's quite easy to change the operating voltage range. And that's what we're seeing is in a lot of this green energy stuff. So if you see like solar panels, the output from a solar panel varies enormously, whether it's in full sun or if it's under shady cloud conditions. And you need a DC-DC or a DC-AC inverter to put this power into the grid or into the home battery. And if you're using wide bandgap transistors, you can actually get, it makes it much easier to design power supplies that have much wider input voltage ranges than what was possible beforehand. And the final reason is a more precise control. If you have a very fast switching circuit, it responds very quickly. So any kind of load transients or voltage transients, the circuit will respond very quickly to those. If there's a short circuit, if you've got cycle by cycle current control, then of course if your cycle is very short, then it will respond to a short extremely quickly, and that may protect your circuit and also the application afterwards. So there's lots of reasons why you would want to increase the switching speed in electronics and power electronics. One of the main reasons is the problems, I should say, when you do this, is the switching losses. I said before that it increases overall efficiency, but of course, every time you switch a transistor on or off, you've got some switching losses. When it's fully on, you've got almost no voltage across the transistor and a lot of current. And when it's fully off, you've got a high voltage across the transistor, but almost no current. And both of these conditions are very low power conditions. So fully on and fully off are low power. But while you're transitioning from one to the other, you've got a loss. And this graph here, this is for power IGBT. You can see what I've done here in yellow is the loss each time you switch. And one of the reasons why you're going to wide bandgap transistors is that you can reduce that loss. So if you go to a silicon carbide, for example, you see this kind of pattern, and you see the losses in the switching here. And you might say, well, actually, I don't see much difference between those two images you showed me, the one of the IGBT and the one of the silicon carbide, both losing power every time they switch. But what you probably is not so clear from these drawings is the scale on the time. And if you put them together, this is what the difference is in scale. So the losses every time you switch on an IGBT can be something like 900 to 1,000 microjoules. And for a silicon carbide, switching the same load will be maybe a 9 times less switching losses. So this really allows you to speed up.
Very interesting. Very interesting. Yeah. So see, okay, that the switching losses are much less for silicon carbide. Yeah.
Yeah.
And
that's what makes them so interesting.
Mm-hmm. So, and when you see here IGBT and also silicon carbide, gallium nitride, so they are in different power levels, I think. Yeah. So can you show something about what is the different power levels to serve with these different technologies?
Sure, that's the next one. You can see here basically here the power and the frequency. So the gray area here is the standard silicon MOSFETs, and basically you can switch very high power with normal silicon FETs. And you can switch at a reasonably fast speed, but really the sweet spot for power electronics is around, for silicon, is around 100 kilohertz. Beyond that, you're starting to get into problems with the switching losses, and also with other problems with the capacitive on the gate drives capacitance on the gate drives makes it very difficult to switch faster. And that's why when you get to higher power, you can see here what's shown in here in purple is the IGBT. So IGBTs are typically, they switch much slower, so 10 kilohertz, but they can switch at a much higher power. So they can go up to 10 megawatts or more. And the reason for that, why they switch so slowly, is that it's very hard to switch them off. You can turn off the gate, but because it's an insulated gate transistor, which is the IG means, it means that basically the capacitance on the gate has to discharge internally, and you can't kind of suck the charge out of it so easily. So if you look at the blue one here, the silicon carbide, you can see that's a much wider range. You can go to much higher frequencies. So you can switch here quite comfortably, actually, up to megahertz. And quite high powers. So at that kind of level, you can switch hundreds of tens or hundreds of kilowatts. So that's what's really interesting. It covers a much wider power range at a much higher switching frequency. And of course, GaN is what everyone's talking about. It can go even higher. At the moment, it's difficult to switch higher power because they just haven't been developed yet. They can switch such high. They can switch high currents, but not so high voltage. So that limits the power levels they can go to. But they are almost ideal switches. So you can have 1 megahertz, 2, 3, 4, even 5 megahertz switching frequencies with GaN.
When you have this high frequency, especially on SiC and GaN, of course there are other challenges you have facing, where during the design. So what are the challenges here, especially?
You can switch them fast, but the problem is all of the parasitics, and that makes a problem. So even small lead, for example, on a TO220 transistor format, the length of that little lead is enough, the inductance of that lead is enough to actually cause problems at that kind of frequency, which is the reason why a lot of the GaN transistors are going towards SMD format, so they can reduce the inductance and the capacitance of all of the connections. Because at those frequencies, it really does make a difference, and it's one of the design factors you have to take into account, the fact that at higher frequencies, you're dealing practically with radio and no longer with electronics or electrics anymore. So you need to really think about how you're doing this.
Yeah.
The other problem is all the other components, like if you have an inductor, and most inductors, especially power inductors, are not designed to run at those kind of frequencies. You need really special types of ferrite that can cope with such a high frequencies, and that's also a problem.
Okay, great.
So there are certain disadvantages when you go to fast switching. It's not so simple. You can't just keep increasing the switching frequency more and more and more to get smaller and smaller designs. You have to take account of all sorts of other problems that might happen. So the first one is obviously if you're switching very quickly, you see higher peak voltages. That means any kind of stray inductances, stray capacitances, leakage inductance and capacitances on the board and everything, these interact with the switching waveform to create ringing and spikes, and it's very easy to destroy a GaN transistor by subjecting it to higher voltage. That's just by the layout, that's enough sometimes to do that, even though your design says that it should function properly. The other thing is obviously this high DVDT, the rate of change of voltages, stresses other components. So there are problems maybe with lifetime with very high speed switching. You may find that a design which will work reliably for tens of years with a low frequency has a much shorter lifetime on when there's fast switching. And also the high DIDT, the current. As I said before, this makes layout extremely critical. You have to be really careful about how you do your layout.
Okay. So thank you very much, Steve. It was very interesting to have this input from your side, and I'm looking forward to our next tech chat, where we want to talk about how to ensure the reliability for fast switching, especially in power conversion applications.
Yeah. I'll go through and I'll go through that and tell you how to do that. Thank you very much.
Yeah, thank you very much. Bye for now.
Bye.